In section 11-3, we'll be learning how to find derivatives of products and quotients. Of course, products are factors that are multiplied together. Quotients are factors that are divided. As we saw in chapter 10, sometimes a rational expression, something that's written as a fraction, can be simplified as long as all of the terms are polynomials. You can probably reduce term by term and then be able to simplify that way, but that's not always the case. As we're going to see, we may have different types of terms or different types of factors that you can't combine together. For instance, we might be trying to multiply a logarithm times something that's polynomial, or something that's exponential. So we're going to have to learn some rules on how to differentiate those. The product rule simply says this: if we have a function that is composed of two factors and we can't just multiply them together to come up with something that's, say, polynomial in nature, then what we would do in order to get the derivative of that function is we would have to take the first factor times the derivative of the second plus the second factor times the derivative of the first. So that's going to be the pattern we have to remember for the product rule. First times the derivative of the second plus the second times the derivative of the first. Now, the quotient rule is a little more complex. And again, if it's possible to simplify this to become something that's just polynomial in nature, that's probably the easiest way to go, but it's not always possible. They are using T and B to represent functions that would be on the top and the bottom. Most instructors who teach calculus teach this as high and low functions, high being the top or the numerator, low being the bottom or the denominator. And so if we have something that's a fraction and it can't be simplified into something that is not fractional in nature, then you will take whatever's on the bottom times the derivative of the top. Notice where we had a plus sign in the product rule, we're going to have a minus sign in the quotient rule. So it's bottom times the derivative of the top minus the top times the derivative of the bottom, but all of it is over the bottom squared. For most calculus students, you may learn this in this fashion. You have low derivative of the high, low d high, minus high d low over low squared. Okay, so it doesn't matter how you think of it. You just have to remember that with the quotient rule, there'll be a subtraction sign in the numerator, and don't forget that you have to divide it by low squared. So low d high minus high d low over low squared. Now, let's practice. And as we look at this first example, notice even though there are two factors, both of these factors are polynomial. So what I want to show you is as long as both factors are polynomial, you have the option of multiplying first, then finding the derivative using the calculus, or you can use the calculus and then simplify the algebra at the end. Usually it's easier to simplify algebra first and then do the calculus. So on this one, I want to show you now notice I'm not going to put f prime of x. I'm just going to put f of x because I'm simply going to distribute, and I'm going to multiply 4x to the 5th times everything in that parentheses. So that would give me 8x to the 7th minus 4 times 13 is 52, x to the 6th, And then if I multiply 4x to the 5th times 2, I get plus 8x to the 5th. This is something I can now differentiate term by term. So if I were to take the derivative of this, 8x to the 7th differentiates as 56x to the 6th. Remember, I pull down this exponent, multiply it times the coefficient. So that's where the 56 came from. The 7 times 8 was 56, and then I have to take 1 away from my exponent. My next term, if I multiply 52 times 6, and there's a subtraction sign there, that's 312 x to the 5th, plus 8 times 5 is 40 x to the 4th. Let's look at the next page. And what you see here is something that, again, we would have the option to do the algebra first and then take the derivative, or we can do the calculus first. Since we multiplied out first on the last one, I want us to go through and practice this product rule. So, if you remember to find the derivative using the product rule, it's first function times the derivative of the second. With the product rule, you add the second function times the derivative of the first. All right, so let's apply that here. My first function, or my first factor, is 4x squared plus 7. So 4x squared plus 7 times the derivative of the second. So if I look in that second parentheses, 2x squared, if I differentiate that, becomes 4x, and the minus 9 differentiates to be 0. So I have done this much of the product rule. I'm halfway there. Now I need the plus sign, and it's time to do the second half. Write down the second factor, which is 2x squared minus 9. And let's multiply it times the derivative of the first. And the derivative of that first factor is 8x. We have to multiply the 2 times 4 to be our new coefficient, and that'll be 8x to the first. So now what we have is two different places where we're going to need to use distributive property. Then we'll see about combining like terms. The calculus is over, now we're doing algebra. So if I distribute everything in this first parentheses times 4x, I'm going to have 16x to the third plus 28x. I need my plus sign, and now I'm going to distribute 8x and multiply it times 2x squared minus 9. So 8x times 2x squared is 16x to the third, and 8x times negative 9 is minus 72x. So if I look for like terms, I have two terms that are 16x cubed that I can combine. I also have two terms that involve x. So putting this together, my derivative function is going to be 32x to the third. Remember, when we're adding terms, we simply add up coefficients, and the variables and exponents don't change. They have to be like terms to be added together. And then if I have 28 minus 72x, that will be minus 44x. There's your derivative. If we had wanted to multiply first using FOIL and then differentiate, do the algebra first, then the calculus, we still should come up with the same answer. And you can double check that to make sure that's what you get. Now on 3, we have an example that is going to require the quotient rule. And the reason I know that is when I look in the numerator, it has a natural logarithm in it. My denominator does not. And not only is it going to require the quotient rule, look at my numerator. I've got a product rule in the numerator in addition to having a quotient rule. So that means I'm going to need to be very careful that I keep up with all of the pieces here. And so we're going to probably need something to help us stay organized. So first thing I want to do is write out my pattern for differentiating the quotient rule, which is, using their notation, we had the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared, or low d high minus high d low over low squared. So what we're going to run into is when we get to the derivative of the top, that's where we're going to have to use the product rule within the quotient rule. So low is x plus 1. Now, the derivative for the high, or for the top, we're going to come over here to the side, and if my function, actually let's call it g of x so we don't confuse ourselves, just the numerator is x times the natural log of x. That's that product rule. So if I want to differentiate it, I have to do first times the derivative of the second. Well, the second is the natural log of x, and we discovered if you differentiate the natural log of x, it differentiates as 1 over x. So there's the first times the derivative of the second plus the second times the derivative of the first. And the first factor is x. If I differentiate that, I get a 1. So if I clean this up, x over 1 times 1 over x just becomes 1 plus the natural log of x, because the natural log of x times 1 is the natural log of x. So back to our quotient rule, we have low times d high, and we just found that d high is 1 plus the natural log of x, minus high. Now I'm going to put a bracket here because I'm going to get several terms that I'm subtracting when I do high d low. So high is x times the natural log of x, and the derivative of the low, if I differentiate x plus 1, the derivative of x is 1. Derivative of 1 is 0, and 1 plus 0 is just 1. So as it turns out, I'm just subtracting x times the natural log of x. Don't forget, though, because we're using the quotient rule, we have to take all of this and divide it by the bottom squared or low squared. So that's x plus 1 in parentheses squared. Now, I've got some cleanup I can do in the numerator as soon as I distribute. I've got to use FOIL on these first two terms here, first two factors, because I have x plus 1, which is 2 terms in this parentheses, times 1 plus the natural log of x. That's 2 terms. So if I multiply those together, x times 1, first times first, is x, plus outer times outer is x times the natural log of x. I'm just using FOIL here. Plus inner times inner, 1 times 1 is 1, plus last times last, 1 times the natural log of x is just the natural log of x. And then we're subtracting x times the natural log of x from that. Okay, if I do some cleanup in this numerator, and there's no reason to expand the denominator right now, what I see is I have a positive x times the natural log of x here that's going to cancel with this negative x times the natural log of x. So all I need to do is combine the terms that I have in the numerator, and that will give me x plus 1 plus the natural log of x over x plus 1 in parentheses squared. Now be very careful. You are done. You cannot cancel out this x plus 1 in the numerator with one of these x plus 1's in the denominator, because you have a third term being added in the numerator. I can't take part of this. I can only take factors that are the same to reduce or cancel. So make sure you don't go too far and you recognize where you need to stop. So now we have another equation, another function that obviously requires the product rule, because g of x is equal to x times the natural log of x. And this should look very familiar because we just worked this as part of the previous problem. But now we're going to find the equation of the line that's tangent to this function at x equals 1. So this is very similar to what we did back in chapter 10. We just have a little more difficult differentiation that we have to do now. Now let me remind you that that product rule tells us, and I'll use some shortcut notation here, that we take the first times the derivative of the second plus the second times the derivative of the first. So let's get started on this by writing down our first factor, which happens to be x, times the derivative of the second. And remember, if I'm differentiating the natural log of x, it differentiates as 1 over x. So we've done the first half of the product rule. We need a plus sign. Now for the second half of the product rule, we need the second, which is the natural log of x. That's our second factor, times the derivative of the first. And since the first is x, when I differentiate it, I get 1. That means that g prime of x, when I clean up x over 1 times 1 over x, my x's cancel and I just get 1, plus, and the natural log of x times 1 is the natural log of x. So that's the derivative. And the reason I need it is because that's my equation that allows me to find slope anywhere on my graph. Since I need to find the equation of the line that's tangent to this function at the point x equals 1, I need to find g prime of 1. That will tell me what the slope is at that point where that line is touching my curve. So in the derivative, I will plug 1 in for x. And here's what I have. 1 plus the natural log of 1. Now remember what natural log means. A logarithm is simply a tool for finding an exponent. And if it's a natural log, the base we're using is e. So this is asking you to find the exponent. E has to be raised to give you an answer of 1. And hopefully you remember that if I raise anything to the 0 power, it equals 1. So the natural log of 1 is 0, and that means 1 plus 0 is 1. My slope at x equals 1 is 1. My slope would be something different if I used a different x value, but at x equals 1, my slope is 1. Now to write the equation for the tangent line, I need the slope, but I also need another point on the line to be able to get the equation. And the point that's going to be easiest for me to find is that point that they share in common. I want to put 1 in as my x value in the original function to see what the y value is. That's going to be the point they share. So if I plug 1 into the g function, I get 1 times the natural log of 1. And we just discussed how the natural log of 1 has to be 0, and anything times 0 is 0. That means the point that they share is when x is 1, y is 0. So that's the information I'm going to need to write that equation for the tangent line. And to get the tangent line, I will plug in to y minus y1 equals m times x minus x1. My y1 was 0, my m was 1, and my x1 was 1. Well, y minus 0 is just y, and 1 times anything is whatever I'm multiplying 1 times, so I get y equals x minus 1. That is the equation for the tangent line at the point x equals 1. All right, 5 is also an example that needs the product rule. And this time, be careful, we really don't have a product rule inside a product rule. Notice that that first factor is 3e to the x, but the 3 is just a scalar or a coefficient. It isn't anything that needs the product rule. We just keep that same thing in the second factor, 3 times the natural log of x. So again, in order to differentiate, we're going to have to take first times the derivative of the second plus second times the derivative of the first. So looking at our function, the first is 3e to the x times the derivative of the second. Since the second is 3 times the natural log of x, we keep the scalar of 3, and when we differentiate the natural log of x, we get 1 over x. We'll clean that up in a minute. And when we do, we can think of 3 as 3 over 1. So we have taken the first half of the product rule, don't forget your plus sign, big plus, and then the second is 3 times the natural log of x, and I have to multiply that times the derivative of the first. Well, my first function is 3 times e to the x, and if you remember, e to the x is the one that's easy to differentiate because it differentiates as itself. It will differentiate as 3e to the x. And now we just need to do a little cleanup here. By the way, we're not writing the equation for a tangent line on this one, we're simply finding the derivative. So if I were to clean up on this first set of factors, I can multiply the 3 here times the 3 here, and 3 times 3 is 9, e to the x over x in the denominator. I'm simply multiplying straight across. I have 9e to the x in the numerator, and then in the denominator, 1 times x is x, plus, if I look at the second pair of factors, again, I have 3 times 3, which is going to be 9. I apologize for the messiness on the way this worksheet copied. And then it doesn't matter the order that I write the other two factors in. I can put e to the x first, natural log of x at the end, or the other way around. So 9e to the x over x plus 9e to the x ln of x is perfectly acceptable. If you wanted to factor out the common factor of 9e to the x, you could do that as well. And that would mean in the parentheses you would have 1 over x plus the natural log of x. So either of those would be just fine. And now we're going to look at an application problem. We're given a function. It says, suppose a factory worker can assemble this many items after T days of training. So this would let us compute the number of items they should be able to put together after they've had a certain number of days of training. Now, the first thing we're going to find is how many items they would be able to assemble on day 5, I of 5. And if you remember what it means when we take a derivative, because if you notice right here it says I prime of 5, a derivative is a rate of change. So we want to find the rate that the number of items he's able to assemble is changing after 5 days of training. We're going to hope that's a positive value, that there should be an improvement from day to day as he completes the training, but we're going to have to discover that. Now, to find I of 5, that simply means we plug 5 into this function. We're going to have 100 times 5 squared over 5 squared plus 7. So in the numerator, if I square 5, that's 25 times 100 is 2500. Over, in the denominator, I have 5 squared, which is 25 plus 7, and that's 32. So if we put this in our calculator and simplify, 2500 divided by 32 is just a little bit over 78, 78.1 something. So it is about or approximately 78 items that he is producing or she is producing after 5 days of training. So after 5 days of training, the worker is producing about 78 items and what we need to find now will be I prime of t. We need to see what that rate of change is, and this is going to require the quotient rule because I have a fraction, there are 2 terms in the denominator, there is no way to clean this up where it's no longer a fraction, so we're going to have to take low, which is t squared plus 7, times the derivative of the high. Well, if we differentiate 100 times t squared, we're going to have 200t to the first, minus high, which is 100t squared, times the derivative of the low, and the derivative of the low is 2t. All of that over t squared plus 7 squared, low squared. So if I distribute in the numerator, what I will see is I have 200t to the third plus 1400t minus 200t to the third, all of that over t squared plus 7 in parentheses squared. And if you're paying attention, you should get a little excited about the fact that the 200t cubed is going to cancel with the minus 200t cubed, and that means we now know what the derivative is. What we need to do is plug in 5 to see what is actually the rate of change in the worker's assembly rate on day 5. So I prime of 5 ends up being 1400 times 5 over 5 squared plus 7 in parentheses squared. Well, 1400 times 5 is 7,000. 5 squared plus 7, we discovered a little bit ago, was 32. And if I take 32 and I square it, that gives me 1,024. And if I put that in the calculator, I'm going to end up with something like 6.7, which is about 7 items. So what that tells me is that after 5 days of training, the assembly rate of the worker is increasing by about 7 items. So that's a good thing. The worker is getting better, getting faster after more days of training.